We're meeting back up again in 5 minutes for the 5-minute talks, and I'm Angie Hodge from the University of Nebraska, Omaha, and I will be emceeing the 5-minute talks. We have 9 on our list so far, so there's room for 1 or 2 more if someone thinks that they might want to be put on that list if there is time. So we'll see you all in 5 minutes, and thank you also to Stan for moderating our last session. Our first speaker will be Travis Mobies. After that, Greg Foley, Stephen Jones, Ted Mahavier, Michael Gagliardo, Greg Macklem, David Bellamy, John Mayer, and Lee May. So that's what I have on my list so far. We'll go down the list. I'm kind of going to run the show like Judith did. When you have 1 minute left, I'll come stand up on the stage, and when you're done, I'll come kick you off so the next person can talk and get their chance to talk. So.
Good day. I'm Travis Mavis. I worked for NASA and SAIC for over 25 years, and now I formed my own company called SIGCOM Sciences, LLC, and I'm the CEO of that. And a former colleague of mine, Hugh Miller, a mathematician from the University of Alabama and also a former football player there as well, for what that might create interest, joined our company not too long ago. We worked together at Texaco for quite some time. Anyway, just recently we've been involved in the Macondo incident, or the British petroleum BP oil spill, as some people probably better know that as. And one of the problems there in people working on trying to predict when blowout preventers will fail is that of doing trend analysis off of trouble reports. Trouble reports are just tons of data, text data, that come in when we are talking about trying to predict a problem that's going to occur. What most of the scientists and the engineers in this area are concerned with is when you have an increase of, or a trend up of certain types of problems associated with BOPs, or blowout preventers. Well, strangely enough, one of the solutions lied buried hidden in pure mathematics, which Hugh worked on this unsolved problem some time ago at the University of Alabama. Now, I know I only have 5 minutes, so I won't be trying to prove this theorem. But the theorem states that a blocking set of a function f is a closed set which does not intersect f, but which intersects each continuous function with domain is the same as f. And what we show in here is that if f is a Darboux function and m is a blocking set for f, then the x projection of m, the common part of m and f closure, is uncountable. And so using that results, we showed that the closure of each function is in class U0, and the closure of an almost continuous function, and obtain a sufficient condition, which is, when placed on a Darboux function, yields almost continuity of that particular function. So with that comes the concept that we were working with. This problem, by the way, was first presented by Dr. Thomas Chapman of the University of Kentucky, Hugh thinks. So we set about and we were proving it. But in the concept of the proof, we got into the concept of a clustering set. And so what we were able to do was to take all these documents we were working with and change them into integers. Simply what you do is you take every word and make it that's in all the documents, and there are thousands of them, and make an integer out of it. And then after you do that sort of in an obvious way. The letter A can be -1, the letter B can be +1, and through the alphabet. And so after we turned all the words into integers, we then took a Hilbert transform and looked at the set like that. And then we applied some of the things that we learned out of this particular working on this theorem, was a way and a technique to cluster the documents together. This gave us a way to see trends by suppressing certain things going up. People don't care if they know there are problems. They know there's a problem with valve A. But the question may be is what causes this trouble? There may be 5 factors, and that's flat. That doesn't trend up. But if you suppress one of those factors and add another one that occurs only occasionally, you may see the trend going up. And of course, there's combinations uncountable almost in putting these things together. Well, anyway, my point is that by using a more approach, which I almost had to since it was an unsolved problem, we were able to also think of these other things in clustering documents. And I don't know if I mentioned this, I didn't, but we use the concept of the cluster set of a function, and that improving this theorem, and that led to the other thing. So my offer.
You off here.
Okay, my offer is if you want to. It was 5 minutes really. I thought I had minutes left. Well, anyway, if you would like to email me, I would be glad to send you a copy of this paper. And I know it's a short and fast, and it's probably a little bit too fast, but anyway, if you'll give me an email, I'll be glad to send you a copy of the paper. Okay.
Let's thank our speaker. Greg Foley is up next, and I'm going to just start the timer as soon as you get up here and give you the 1-minute warning. So I apologize for that as we get everyone through.
I want to talk to you, give you a project update. Advanced Quantitative Reasoning is a course for high school seniors, an inquiry-based course. Kathy Seeley said that perhaps the worst thing that can happen to a student at the end of his or her secondary mathematics preparation is to enter college not having studied mathematics after a lapse of a year or more. It's a major problem in the U.S. A lot of kids sit out their senior year. Many of you teach freshmen and know that they come in somewhat stale to mathematics. So as I said, this is an inquiry-based course. It's in mathematics, statistics, and modeling. We don't do modeling quite as sophisticated as the previous speaker, but it gets students prepared to do those kinds of things in later life. The core of the course are motivating questions and engaging investigations. Most textbooks are not written in an inquiry-based mode where it's questions for students. There's worked out examples, and then the problems are at the end of the lessons. This includes problems throughout the lessons. And it's divided into week-long chunks of material, so there's a little bit greater depth than is typical. There are several goals to the course, including quantitative literacy, ability to communicate, and to prepare for post-secondary work. The 4 units of the course are numerical reasoning, statistical reasoning, modeling with discrete and continuous functions, and geometric modeling and spatial reasoning. And students not only do quick questions, explorations, and investigations, but also projects and presentations. To give you an example of the nature of the course, here's a problem that students would do related to Zipf's law. Which states that the largest city of a country is twice as big as the second largest, 3 times as big as the third largest, so the 4th largest city would be 1/4 that of the largest. And so you'd look at actual data, and so we would expect Austin, which is the 15th largest city, to be 1/15 the size of New York. And it looks like that may be so, but then to delve deeper, what are the explanations? How good is the fit? How would you measure that? What case could you make for whether you think that this law fits and to what extent it fits? If you're wondering where Ohio University is, it's in Athens. And that's where the location of Athens. This is a problem from the first section of the book, is to use an orange to model latitude and longitude. The L there is London on the prime meridian of the orange. The cutoff there is hard to read, is Quito, Ecuador, which is on the equator. And Athens is north of Quito and west and slightly south of London. And this is, there's a related problem to this. In spherical geometry, if you're traveling from Athens, Texas to Athens, Greece, will you pass closer to Athens, Georgia, or Athens, Ohio? And so this is turns out to be an interesting question, and even a lot of the teachers that we have in related professional development are surprised by the answer to this question. The 2 programs, we have 2, I'll be running starting Monday, a 2-week Institute in Probability and Statistics for teachers, and later this summer, ModSpar, and these in modeling and spatial reasoning. And these are designed to help get teachers ready to teach such a course. And sort of is in response to Paul Sally's question about content related to the Common Core. And since my time is up, I will just quickly say thanks to folks. Thanks to EAF for sponsoring this conference. And if you need to contact me, here's my information. Thanks.
Thank our speaker, and Stephen Jones is next, and Ted Mahavier after that.
Thank you. I'm Stephen Jones, and I'm here actually just to make some comments and observations. I have nothing prepared, and before I do, I have to give you a little of my background so you can understand where I'm coming from. In the early 60s, I took 11 courses from Dr. Moore as an undergraduate. I went to Wisconsin and got my PhD from Dr. Bing. I was at the Institute for Advanced Study for a couple of years. I taught at the University of Massachusetts, and then I went to law school at the University of Michigan and have been a lawyer in Los Angeles for the last 35 years. I thought that the Moore method had died until about a year ago. I suddenly heard about this organization and decided to come down and see what this conference was about. This afternoon I'll be on a panel, and I will hopefully then talk about use of IBL in teaching of law, but I wanted to make another observation today. And that is, a lot of the focus that I've heard today is teaching the IBL, the Moore method, for students that are going to go on to higher math, to chemistry, to physics, and so forth. And I thought that that focus is myopic. It would be difficult to convince you of the rational thinking and mathematical thinking that lawyers and judges are totally idiots of. No one should graduate from college not having a course in rational thinking. It turns out deductive thinking is not natural. You have to be taught that. Inductive learning is what everybody seems to do. Now, I have a rule when I read an opposing brief for the first time. I have to be in an easy chair, and I have to have a large glass of scotch next to me. The fallacies, the illogical syllogisms, the errors that are contained in there are outrageous. And it just makes me angry, and I have to have a drink of scotch. Then the thought occurs to me, could the judge possibly buy all this? And then I need another glass of scotch. Now, how can we teach these people to think? And I don't care how it's done. They shouldn't graduate from college without having a course in it. And there are a number of ways you can do that. Those people that know me would understand when I say, well, you could do that with a course in chess. But you try and sell that to the administration, and it won't work. The only discipline for which is presently in place the ability to teach people to think is mathematics. And the Moore method is the only one that does that. And now the question is, what class should they take? All right. Now, first is, my theory about classes, you ought to ask, what's important about this class? Is it the destination or is it the journey? Now, if you're going to have people, you're going to have history majors and so forth, you're trying to teach to think, you don't care what they learned actually, you care that they learn to think. So the destination is not important, the journey is important. Also, if you try to teach a Moore class in calculus, let's say, that's going to be intimidating to your history majors. That's calculus, and you're trying to teach me calculus, and you know I'll never learn calculus. So my strong recommendation for a class, and I would love to see it required of all graduates, is a geometry class. That's less threatening. You have the Moore class that he took in geometry. You have the geometry class we heard about last night. I urge that these classes be taught not just for math majors, but for everyone. The question is, How do you get the administration to go along with that? How do you get people to sign up? Well, that's your problem, except I'll say one thing. The piece de la resistance to get them to do this is to hand them a copy of any LSAT test and tell them to look at the type of questions that are on there and see the type of reasoning that the students need to make good scores on the LSAT, and that'll get you a long way toward that. Thank you.
Thank you. Ted Mahavier is next, and Michael Gagliardo is after him.
Thank you, Angie. Thank you, Angie. Can I have the Elmo? I was informed that I was originally scheduled to give 2 back-to-back 5-minute talks. I'm not sure what this says about the management's estimation of you, but they said they didn't want to give the false impression that someone was given additional time. I'm not good at estimating things either. The website there is a webinar that demonstrates the teaching of my father, the late W.S. Mahavier, in the fall of 2008. It was the last course he taught, and he taught the Moore method all my life. I estimated that project at a few hundred hours, maybe 300 hours. It took around 1,500. I wanted to make you aware of that resource. I don't know there's a link to it anywhere on the web, so I don't know there's any way to get there except to write that website down. 16 years ago, 2 professors did something that only assistant professors can do. They decided that helping 100 students a semester wasn't near enough, and they co-founded something called Math Nerds to help people all over the world. This was when the internet, this was before some of y'all were born, this was before the internet was born, and we were one of the first help services on the web. We still remain the only help service on the web that doesn't give the answer. However, we have outgrown Math Nerds, or Math Nerds has outgrown us, and we are looking for a new home, new management. For the math educator, there are over 200,000 question and responses, some of which go back and forth 200 times. There's an enormous amount of data here for someone who is interested in the project. The project itself basically consists of the free question and response service, the website itself, and the question and responses, and a few other softwares. If you are a tech-savvy person who wants a very exciting project, this one needs new vision. We will be shutting it down within the year, whether it's taken on by somebody else, if it's not taken on by somebody else. So I just wanted people to know that this is an available opportunity for them. And I can take a question because Angie's not standing yet.
Because there's a lot of history I just found out that's getting lost. For example, it seems that I just heard that Project Next was having trouble finding out its history. And I'm on a project to the history of the Sigma on Room right now, which I participated in, so it's more chance I could do something with it. But anyhow, it's a pity to lose it. It should be somewhere.
I concur. 43, 42. Thank you.
Let's see if I get your name right this time now. Michael Gagliardo. Oh, man, I can't even say it, even though Judith says it a few times. Why don't you say it so I get it right next time? That's what I have my students do like 7 times. And then Greg Macklem is next.
So my name's Mike Gagliardo. I have terrible handwriting, so that's one of the reasons everyone's saying it wrong. I finished my first year at Cal Lutheran University after spending about 4 years at a small school in Florida. And I wanted to talk a little bit about a geometry class I just taught this past semester. My department sort of forced a textbook on me, which turned out to be a really good thing because I enjoyed the book. It was Experiencing Geometry by Henderson and Tamina. And it's not a new book by any means, but it was new to me. And I really enjoyed the experience, and I think the students did too. So I just wanted to talk a little bit about that. First, to set up the class, it was a writing-intensive course, which means there were 3 papers. It had a history component. The only prerequisite was Calc 2, and there's no guarantee that the students had a proofwriting course. And this was not our Intro to Proof course. So it was some of them were very inexperienced in their mathematical maturity. So some of the things I want to talk about, I'll start with sort of the selfish reason I liked it. One of the things I noticed going from graduate school being a differential geometer to teaching undergraduate geometry courses is I felt a major disconnect between what I felt geometry, active geometry was versus what we're teaching in the undergraduate level. Euclidean geometry doesn't really come up much in graduate school. It's about manifolds and surfaces, connections, vector bundles, and things like that. So I had noticed this disconnect, and the book does a really good job of bringing some sort of 20th century viewpoints of Euclidean and Hilbert geometry into the class. So for instance, they do talk about parallel transport and holonomy, and all of it's from a very intrinsic point of view, from the point of view of being on the surface, much like differential geometry is, the intrinsic view of the manifolds. And again, this is all done with Calc 2 as the prereq, so you're doing all of this without equations. You're doing it rigorously, but you don't need necessarily the year of graduate geometry to approach this. It also goes through some of the applications, like applications to navigation, shape of space, background radiation, so applications to physicists. Now, the reason where the Moore method, or the IBL, comes in is students actually start with creating their own definition of a straight line. The first question in the class is, what does it mean for a line to be straight? Or in other words, define a straight line. So you get to talk about what is a good definition, and you start from there. And then once they feel confident in that they have a good definition of a straight line, you hand them a sphere. And you say, does your definition work on a sphere? And of course it doesn't, because that's not what they were thinking of. And you adjust it and you try to make it general. And you continue on with this idea, and they get a very intuitive idea or intrinsic view of why great circles are lines and so on. So you're talking about geodesics and these ideas without actually having to go through the definitions of connection and so on. And then students go on to prove theorems using their own definitions as a starting point. And then once they have their first set of theorems, everything gets proven from that. They prove classifications of isometries, equivalence of parallel postulates, and depending on your requirements for your course, there are many different aspects. And one of the things I really liked about it, and the students liked it too, is the view of parallel through parallel transport. And all of this there's very little lecture. All the students are exploring all these different activities and bringing up their proofs. I still have time, okay. And for those of you who've had differential geometry, you know that parallel transport is a fairly difficult concept with a lot of equations, but the nice thing is it really shows the separation between spheres, hyperbolic geometry, and the plane, and shows how the plane is really the unique one, and elliptic and hyperbolic are not the strange ones. But anyway, the other thing is the students really seem to like the course. The evaluations read, 8 out of the 9 students liked the course, let me put it that way. The 8 that liked it, evaluations read as if I was writing a brochure for IBL. The one who didn't like it, surprisingly, their evaluation also read like I was writing a brochure for IBL, things like we had to come up with ideas on our own, and things like that. So I just know there's been a few geometry courses or geometry books spoken about in this conference, and this was one that I think takes for geometers who want to show some of these ideas of manifolds and surfaces and things like that. This also is a pretty good book. All right, thank you. Experiencing Geometry by Henderson and Tamina.
Thank you, Michael. Greg Macklem is next, and then David Bellamy after that.
Good afternoon. My name is Greg Macklem. I'm the Society Coordinator for the History of Science Society. And I'm hoping in a minute we'll have our website up there. The URL is www.hssonline.org. It is an international society of about 2,000 members, individual members, dedicated to the study of the history of science, and that includes the history of mathematics. And we also have a very active forum for the history of the mathematical sciences, which is headed up right now by Karen Parcel from the University of Virginia, who is here for this conference, as well as Albert C. Lewis from the Educational Advancement Forum. So I would encourage any of you who have any interest in the history of mathematics to certainly check it out. We have 2 upcoming conferences, one in Philadelphia and then one in San Diego. We would certainly love to see all of you attend and enjoy with lots of scholars, many of whom are interested in the history of mathematics. However, being here, my own background, I came from a 9-year teaching career in junior high and high school mathematics. And so even though we're planning these 2 conferences, I find myself really fired up to go back to the classroom. Just don't tell my boss about it. It might not be a very pleasant welcome for me when I get back. I'd like to, I guess I feel like I do need to make, or should make, some sort of contribution to a lot of the discussion that's going on here. And as a teacher, mostly in calculus, but also even in 7th grade math and in geometry and some other lower level courses, there certainly is a very vital role for IBL to play, and I did try to do that. And part of that came out of my own training. I'm a proud alum of the University of Michigan, and I'm very pleased to see my alma mater so well represented here. And I wished that during my actual math education had some more exposure to IBL. I got some of that in my education training and tried to bring that into my own classroom. And as a representative of the History of Science Society, I thought it would be useful to point out there are plenty of episodes in history, whether it's just history of mathematics specifically or history of science or broader history, that I think, and from my own experience, can be used very effectively in the math classroom. So 3 in particular that I have used and wanted to point out as potential uses, as potential episodes to consider. Again, this might be more effective for pre-college courses, but that certainly depends on your setting and what you think would be appropriate. The first one I used to actually start in probability and statistics course before we did any probability, and I've actually used this a little bit with younger kids who haven't had as much probability experience, is to actually pose the problem, or a similar problem to the one that Pascal and Fermat discussed, that sort of kicked off this whole idea of probability. So if you have a game setting, or say it's a best of 7 playing dice or something like that, and you have 2 people competing, and one is up 3 games to 1, and then to say going to a 4th game, if you have to win 4 to win the series, and there's money at stake, and the game has to end for some reason. What's a fair distribution of that money? Well, that gets into discussions of probability, gets into discussions of expected value. And for students who even have some basic idea of probability, they'll start discussing this without necessarily realizing that that's the same sort of idea as pulling colored balls out of a hat, which is where a lot of them get their initial exposure to probability. So that's one situation where an episode in the history of mathematics can be used to great effect. In graph theory, which I taught as part of a discrete math course produced by, out of a textbook produced by COMAP, if I remember correctly, is the 7 bridges of Königsberg, which Fermat used to really essentially prove the first theory in what became graph theory. And what I did is I simply put the problem up, showed him a picture of the bridges, and gave the problem. Said, is it possible to cross every single bridge exactly once without, and ending up right where you started without crossing a bridge twice? Well, eventually, after enough discussion, enough work together, they will come to the realization that no, you can't. And they will come up with a verbal explanation, such as you have to have both a way in and a matching way out, unique way out off of every landmass, which gets you into essentially the idea that Euler was able to prove. And the last one I used to great effect, actually in 7th grade math class, is simply images of the Alhambra. If you've ever seen the tessellations there, and using those sorts of images to get into basic geometric ideas, in particular with angles, giving students a chance to explore angles, opposite angles, adjacent angles, what relationships do they have, and start to explore what angles match each other, congruence, ideas of adjacency, complementarity, and so on. So it looks like my time is up. I thank you very much.
Thanks.
Thank you. David Bellamy is up, and then John Mayer after that.
Someone at one of the 5-minute talks this morning asked a question. About an hour later, I realized I had a suggestion for an answer to it, and then I also realized I didn't remember who had asked it. But then it occurred to me that, well, there might be other people who were interested in the answer, so I thought this was the appropriate venue. The question was, did somebody have a suggestion as to how you could get teaching assistants who met with students once a week to use an IBL-like technique or techniques in small discussion sections in, for example, calculus or beginning discrete math or something. And I realized that I have a rather crude, but I think fairly effective system that has worked very well that I think fits into that description. And that is that, and I have had a few teaching assistants who've balked at it, but mostly it has worked quite well. And that is, I tell my teaching assistants, unless I specifically tell you that I want you to discuss a certain topic and lecture on it briefly in the discussion section, I want you to do nothing of the sort. Pick maybe 7 or 8 problems, maybe a dozen, preferably even-numbered problems, though it doesn't matter too much, and have the students sit down at their desks. Their option, they can work alone or in pairs or even trios, and you just walk around and watch what they're doing and give individual hints and coaching for the entire 50 minutes or 60 minutes that you have them in your class. And you can and they get 1 point. The students get 1 point in my grading system just for attending this section, so they will stay and work on it, and it has worked quite well in getting students to actually have a little stimulus to come alive mathematically and work on problems in the setting with the teaching assistant giving them coaching if they run into snags or something. And I found this works wonderfully. It's not perfect. It probably gives a little too much help to the students, and they don't recognize the beauty of having to struggle with something for 4 or 5 hours before they get it, which is important. But I found it helps a lot in this regard. And the teaching assistants, once they learn to learn to deal with it, actually like it, because basically all they have to do in the way of preparation is choose what problems from the sections we're working on to pose to the class that day. So, thank you.
Thank you, David. John Mayer's next, and then Lee May after that.
David surprised me by being the soul of wit. I wanted to talk to you briefly about 3 assumptions that I hear made both within and outside the IBL community. IBL is so broad. In fact, David just gave us an example of how broad it could be. There are many dimensions along which you can have inquiry and learning. These are 3 assumptions I think should be subjected to rigorous what-if analysis. And by that I mean that we should think about alternatives to them and then figure out ways of scientifically testing the alternatives. And I think that would do the IBL community a lot of good. The first assumption is that IBL classes are small. I'm not going to define small, but it is probably not 1,000. I think, however, it might be that you could have a very effective IBL class of some sort with 50 students. And we certainly have already heard today that 20 or so might be ideal. I think that the assumption that IBL classes are small ought to be subjected to rigorous what-if analysis. Secondly, I hear the assumption, and I think we'll see some counterexamples of it later in this conference, the assumption that IBL classes, or IBL is only for the brightest lights. I think that also needs to be subject to rigorous what-if analysis. And by that I mean, again, setting up a scientific experiment where we can see whether this statement is actually true or not. Thirdly, and this is the one that I struggle with most, that students learn more is ample justification of IBL. Now, if you've ever talked to a chair or a dean or even to a colleague, you probably have not been able to convince them that the fact that students learn more is ample justification. They might have reminded you of the example of Alexander of Macedonia, who had a highly paid tutor and did very well for himself. But unfortunately, most school systems and most universities are not in that position. And so, again, I think we need to subject that assumption to rigorous what-if analysis perhaps by showing that there are other justifications for IBL, such as retention, graduation rates, success in course trajectories, and other things that can be established rigorously. Thank you.
Next up is Lee May and then Anna Spice.
I am Lee May, and I'm a counterexample to the statement that IBL works well only for the brightest. This report is in the form of a request. Would you be willing, within 2 weeks of the end of this conference, to receive an email from me? The email would contain essentially one question. Should Lee May record on video one of his Moore Method courses? Let me explain. 3 years ago, the MAA published The Moore Method, A Pathway to Learner-Centered Instruction. The book was the product of the joint efforts of Ted Mahavier, Charles Coppin, Ed Parker, and myself, under Ted's leadership. It is an exposition of the way in which each of us practices his version of the Moore Method in the mathematics classroom. During our writing of the book, it occurred to me that video offered us an opportunity to supplement what we were saying in our writing. For example, I thought it possible that some people who read the book without ever having sat in on a Moore Method class would desire more immersion in the method before reaching a conclusion about whether to try the method themselves. The best way to obtain such immersion, in my opinion, is to sit in on a course taught by an experienced practitioner of the method. For those unable to do this, viewing a video chronicling an entire term of such teaching would be a suitable approximation. I shared my idea with my co-authors, and 2 of them have already had themselves filmed. You might wonder then why I believe that another video, namely one of me, would be needed. The reason is that each of the 4 of us practices the method in a distinctive way. During the writing of the book, it occurred to us that a reader might well identify with, say, Ted's practicing of the method better than anyone else's. For that reason, such a person would want to focus on Ted's remarks within the book and to see a video of Ted practicing what he preached and not any of the rest of us. Therefore, I thought that it would be worthwhile to have a video of each of us. When I attempted to make my contribution to the effort, however, I ran into a snag: resources, or the lack thereof. My university has no one on staff with both the expertise and the time to direct a filming project of the sort that I want to undertake. Neither does it have the funds to outsource such a project. To realize my hope, then, I need to become my own producer, and to do that I need help and time, both of which cost money. I've submitted a concept paper to the National Science Foundation and received an encouraging response. To make a full application, however, will require a year-long effort. If at the end of that, NSF funds the project, another year or 2 will be required to film the course, edit the recordings, and begin distributing them. Although I haven't seen the finished products of Ted and Ed, I'm sure that they are outstanding. The question then is this: is there any use for a 3rd video of Moore Method teaching by one of the 4 authors, specifically by me? That would be the subject of my email to you. If you would be willing to receive an email from me asking you this question, would you raise your hand? Okay, thank you very much. I will send it out. You don't even need to respond to it. If you're not interested, just delete it. I'll look at the responses that come back. If I don't get very many, I'll know the answer to my question. If I get a fair number of yes responses back, then maybe I'll proceed with the project. Thanks a lot. You've already been a help.
So Angie had to step out for a minute. Our next speaker is Anna Spice, followed by David Cusick.
All right. Good afternoon, everybody. My name is Anna Spice, and I'm here to share with you my experience with IBL. Well, rather experience. What I've learned in these 2 years teaching an introduction to proof class inquiry-based style. And I think the theme pretty much has been that nothing is really what it seems at first. And this is not just for the students, what I try to convey to the students, but also it's something that applies to myself. And what I'm trying to say here is that there are lots of surprises in an IBL class, and just giving the students the power to kind of lead in a sense is going to make very. It's going to surprise you. It's going to amaze you. Sometimes you might want to cry, but often. It's really good. And I just wanted to tell you a little bit about how I structured my intro to proofs over these years, and I've been changing it constantly pretty much, and that's, I think, one of the most fun parts of my job. And so we started, for example, most of the things that I picked up have been suggestions of previous workshops. So I'm really indebted to the organizers of all of the IBL conferences. So we get started like breaking the ice with some exercises, and the inspiration for this one is Carol Schumacher. She's got a beautiful true-false exercise at the beginning of her chapter 0. And so that's the very beginning. So true-false questions, the students is the first day of class, just get them involved and getting to know each other. And the thing is that they kind of answer questions like, is this true or false? Is it always true, never true, sometimes true? And the questions are not as easy as they might look like, or some of them are really easy, but sometimes I throw in things like, this is not a sentence, or the next one is not a sentence, things like that. So that is a little bit of a challenge, and they start thinking, oh, this is not going to be as easy or as straightforward as I thought this class would be. And then we keep going. After these true-false exercises, I have a lot of group work at the very beginning, and then it kind of transitions in a more traditional type of more method class with the student presenting at the board. And in this group work, for example, we talk about syllogisms, like Lewis Carroll's exercises. I mean, the nice puzzles that he's got, and then from there we start talking about logic and how everything kind of follows. I really liked an idea of a course that was smoothly transitioning from one thing to another. And then we cover things like sets, like many introduction to proofs classes. I don't do truth tables because I don't like them. And another thing, but I do something between truth tables and Venn diagrams, which are characteristic functions. So that ties everything all together. We do Boolean algebras, and let me Boolean rings rather, and let me show you why. Essentially, so we can play binary Sudoku. That's why we do Boolean algebras or Boolean rings. And then students start proving things like, a Boolean ring is commutative, all of that kind of beautiful stuff. And it kind of lets them start thinking more abstractly. And that is really wonderful, kind of getting them in the idea that it's not just x plus x, which is equal to 0, whatever that is. It's not the name that you give to the variable. And then we got stuck at some point in a theorem, and I told them, look, what's the definition of Boolean ring? And they said x times x is equal to x. Okay, good. So an orange times an orange is equal to an orange. And then this is my students. We had an epiphany. Oh, so minus an orange times minus an orange is minus an orange. And that led them to prove actually one of the theorems. One of the group work that we did also, this is a writing intensive class, and we had like a group project. I think students don't really know what it means to be a mathematician, to be a professional mathematician. And so what I gave them to, as an exercise was to interview faculty members at the department and ask them, what do you think a mathematician does with their lives, and then present what they found. All different groups had to interview different people, and then all together the last day they had these small presentations, and I think the final slide of one of my the group presentations, I thought kind of sums it up very well. And so this was their conclusion. This is my a picture. Sorry about the quality, but this is, I take pictures of everything that goes on at the board, work in progress and everything. And we have a class picture of every student that goes on the class, what we call a class journal. And so they concluded, we are mathematicians. I thought that was beautiful. All right, thank you.
I'm David Cusick from Marshall University. At the moment, and for quite some time, I've taught calculus on down to college algebra and trigonometry, so I'm not teaching the high-level stuff. I have some suggestions, and that's all. On the first day in every class, I try to have students stand up, mill around, and greet each other, get some names down, and just break the ice. They're going to be on teams, though they don't know it yet. Earlier today, colleagues Guerra and Benito, Jill and Catherine were talking about teams and assigned roles, and it occurred to me that I do have a suggestion. Though I only keep teams briefly, I create them using playing cards, and from their point of view, if they wish to do that, you could create the teams basically by the ranks of the cards, ace, 2, 3, and so forth. Assigned roles within the teams if you wish to assign them by the suits of the cards. As I said, my groups are brief. The cards are easy to come by, so that was anytime I lose the things, it's easy to replace them. It's easy, quick, and random. It's also good for seating students in exams if you like to have them randomized and unable to look on each other's paper. Let's see, the last suggestion is how I handle board work. Students themselves nominate the questions from previous day's homeworks. I ask for volunteers. If several people volunteer for an individual problem, I ask them to go up in a group, give me one solution to the problem, which means they're up there talking to one another, trying to reconcile their individual points of view. It's safety in numbers, and after I'm able to figure out who in fact is working on the individual problems, which are all happening in parallel, I ask the rest of the class to walk up to the board and watch what's going on for a minimal amount of credit, somewhat less than the board workers are having. I find this one way that helps me to do IBL light, I guess, and I thank you for your attention.
So now you have me a little unprepared. Angie's not back. That was the last name on my list. Are there any, and we have 5 minutes to go. So are there any other last minute, 5-minute speakers? Okay.
Hi, hello. I'm Steve Brown. Last time I gave a 5-minute talk, that's about all I said in the 5 minutes, except I did say, hello, how are you, in 5 different languages, and then I realized the time was up. So I apologize, I won't do that again. Did I tell you what I did last time? I didn't. Oh, okay. Well, anyway, we have heard a number of interesting variations of the Moore method, and I just thought of a variation that I think is simple, but is not so much of doesn't raise so much of an empirical question, like can we teach this with a larger or a smaller number of students? Or do the students have to be really bright, or can any really talented, or can any students handle it? But it's a conceptual question. The basic model presents students individually, in groups, however it is, who come to the board, which brings us back to the 19th century. I don't know why we always have people coming to the blackboard. I thought we were finished with that. But come to the board, and they come up with, the goal is to come up with a solution. And my thought was, what an interesting variation that I think would be in the spirit of R.L. Moore, would be to present students with a solution and have them figure out what the problem or problems could have been for which that was a solution. I have other kinds of thoughts about that also, but I think it would be very interesting to do some sort of conceptual analysis. And I think if we carefully try to vary some of the elements of the kind that I just mentioned, I think we're going to find out that we notice some things about the R.L. Moore method. What are the sort of the fundamental aspects of the method? We're going to notice things about the method that we had never thought of before. Thank you.
So if you were my class, I would tell you that we don't always get out early. But just this one, oh no, so Brian's volunteering, but if you don't run fast, it might be 4.5 minutes.
So there hasn't been much talk of technology this week, which is fine. But I do love technology and Technophile. And there are a couple of interesting ways that I think it supports the way that I do IBL. First, my students turn in a lot of the work that they do in preparation for class through our online course management system. We use Moodle, Blackboard, whatever. Which they turn it in about an hour and a half before class, which is one of the ways that I'm able to have a sense of what's going to happen. So while I was up here on the panel, I talked about sort of knowing in advance what's likely to succeed. So that's one way that technology could support. A second, I should have brought it with me. If you've ever heard of a live scribe pen, it produces a nice set of notes. It's something written, and it simultaneously captures the audio. Yeah, Mike's holding mine up right over there. It just looks like a big pen, but I use it to capture the audio in class. So when somebody's presenting, another student is taking notes, and then I upload these somewhere the students can get to them, and it changes how stressed out they are about taking notes during the discussion, which I find very productive. And then the third major way that I use technology is, instead of having the students individually finish super polished versions of every single item, they often collectively write something together. So Elizabeth Thorin and I have been calling this a wiki textbook, where they take the content that was a sequence of questions and theorems, and they turn it into something that looks more like a traditional textbook, a product that they can take away with them. It's moderated as a wiki, which deals with all the users. Many of them have tech capabilities. It's collaborative online work that mirrors the collaborative in-class work, and I just think it supports the kinds of things I want them to be doing outside of class. So technology.